Hello, and welcome to our fourth tutorial about MBX. In our previous tutorial, we went over how to install MBX plus LAMMPS. In today's tutorial, we're going to show you how to use MBX plus LAMMPS on some of our examples. Today, we're going to go over 3 examples of MBX plus LAMMPS. The first example will be MB pull in a 256 water box. In our second example, we will do the same thing, but we will also print out the dipoles. The dipoles are useful if you want to do analyses such as vibrational spectroscopy. And our third example will be a hybrid example, where MB pull will be embedded inside a larger framework that is instead simulated with classical force fields. If you want to skip to a specific example, feel free to use the timestamps on screen to skip ahead. Alright, so first thing we need to do is to navigate to where our examples are located. So if I do ls, I can see I have the lamps that I previously compiled in the previous tutorial. So I cd into that, and then our examples are located in examples, packages, MBX. And so today I'm going to demonstrate 3 different examples: the pure water box, the water box where we print the dipoles, and then our hybrid simulation where we have our MB pull water in a classical framework such as a MOF. Okay, so for the first of these examples, I'm going to cd in, and we're going to talk about these different files and make sure we understand how to configure our simulation. So first up is the initial.data, and this should look very familiar if you've used initial.data for other LAMP simulations. The only thing to note about this file is in this atoms full, while there is a column that contains charges, do note that by default MBX does not read these charges when it performs the simulation. The charges are instead something that's stored inside the MBX library, and this column is usually ignored. So just keep that in mind. If you try to modify this column, it will not by default reflect into MBX. Okay, next up is the MBX.json. We've gone over this in some of our previous tutorials, so I'll just highlight the ones most important for MBX plus LAMMPS. At the top, notice that we do not need to specify the box for MBX plus LAMMPS. This data is instead held in the initial.data file that we just saw. If you are running a periodic system, you'll need to check that the real space cutoff is set to something like 9, and that the alpha Ewald elec and alpha Ewald disp are set to 0.6 when using periodic boundary conditions. In the event you are using non-periodic boundary conditions, you'll need to change these values such that the real space cutoff is something large like 100 angstroms, and that the alpha Ewald elec and alpha Ewald disp are instead set to 0. This ensures that everything is calculated in the real space and not the k-space. And then, depending on what you're trying to simulate, you should double check that the 2-body and 3-body cutoff is set properly. Since this particular example is using just MB pull water, the 2-body and 3-body cutoff here is appropriate, but if you're using a system such as one that contains ions or some of our other models, you will likely need a larger 2-body and 3-body cutoff depending on the model. Okay. Now that we've looked at those 2 files, we're going to take a look at MBX, the configuration file for LAMPS. Okay, so we're going to go line by line here just to make sure we understand what we're doing. The first line is the processor's line. If you are using MPI in conjunction with MBX plus LAMPS, this command just tells LAMPS to divide the simulation box amongst the different MPI processors as a function of the coordinates. For this simulation, we're using units real and atom style full, and as mentioned previously, we're using periodic boundary conditions so that the boundary here is set to PPP. We then read in the data file, the initial .data we went over a few moments ago. And then here we specify that the pair style for this simulation will be MBX, and that the real space cutoff will again be 9 angstroms, and this should match what's in your mbx.json. Here we've added some bond and angle coefficients. By default, MBX and MBPol has flexible molecules, but in the event you want to constrain the geometry using shake, we've just specified here the bond and angle parameters for MBPol water if you do want to constrain the geometry. For the pair coefficient line here, this is the most important line so that you can configure MBX based on what molecules you are trying to simulate. So here we have 2 stars. Since this applies on all atom types, we have one type of molecule or monomer, and that monomer name is H2O, corresponding with MBPol model. And then in order to connect LAMMPS to MBX, we need to specify the atom types. So for H2O, we have it coded so that the atom types have to go OHH, which is why we then specify 122 to correspond with LAMMPS's OHH atoms. And then here we specify that the JSON file will be called mbx.json, and that's the JSON file I showed you a moment ago. We have some neighbor commands. We have the time stat set to 0.5 femtoseconds per step. This makes sense when using flexible MBX. And then down here, since MBX is a many-body model, you need this compute line to make sure that it computes all the many-body effects for this system. So we tell MBX, all pair MBX will be computed here, and we can extract some useful values if you want using these variables. So if you want, you can print out these extras such as the pip energy, energy of dispersion, Buckingham, permanent, induced, total electrostatics, and total potential energy if you want. We then have 2 fixed lines. This one that's commented out is the fix shake if you want to constrain the geometry. And then the next fixed line is saying that we're doing an NPT simulation at room temperature, 298 Kelvin, and a pressure of 1 atmosphere. The next 3 lines, we've decided here to reset the velocities. You can comment this out depending on what you're trying to simulate. Then we specify the default thermodynamic output, such as potential energy, total energy, kinetic energy, etc. In contrast, we have a commented out line here. If you want to print out even more information, you can use this verbose MBX thermoprint, and this prints out some of the more detailed energies if you want to print these out and do analysis on them. Scrolling down further, we have commented out some trajectory dump commands if you want to turn those on and dump the trajectory. We have commented out the restart. For this example, we will run for only 100 steps, but of course for real simulation, you will likely want to run much longer. And then commented out here are the write data and write restart at the end of the simulation. Okay, so we have now gone over all the files that are needed to run the simulation. Before we actually run the command, something you should do in almost all cases is export OMP num threads so that you can tell MBX and OMP to use more than one core. So for example, on this system, I'm going to use 8 cores. If you don't specify anything, be cautious because depending on how your system's set up, it might default to using 1 core, which is very slow, or it might default to using all the cores. That might not be something you're expecting. Okay, so for my system, I'm going to say 8 cores, and then I'm just going to navigate to the build directory and get my LAMMPS executable that I compiled previously, and then I pass in the in file. So we've looked at all the files, we've set the export OMP num threads to a value that we want, and then here we have the LAMMPS executable, which we're running on our input file. So I hit enter, and we're going to run the simulation. All right, our simulation finished. We were able to look at the performance. So on my local computer, I can see how much performance I get per day based on the number of OMP threads I'm using. And I can verify that the CPU usage is roughly what I expect based on the number of OpenMP threads. And I, of course, can also see the total wall time here. Okay, and so that's our example for water. Do note that in this folder, you have the log.lamps that you have just generated. We also have an example that we've run of the log file so that you can compare that if you ran the simulation the exact same that we did, you can verify that the output matches your log file. And assuming that they match or are very close with only like a decimal or two different, that means you've done it successfully. Okay, so now I'm going to navigate to our next example, which is the 256 water dipole. And so the files here are mostly the same. The initial.data and JSON file is the same, so I'm going to not go over them again. And instead, I'm just going to go into the LAMMPS file, skip all the portion I talked about a moment ago, and we're now going to go here to the dipole moment. So this section extracts from MBX the original, which is the total, induced, and permanent dipoles that MBX is printing out. And then here we're doing some unit conversion of the dipoles. And then down below, we now have this new dump, which will write a new file called dump.dipoles, which will include the coordinates, but also the components of the dipoles printed out like this. And do note that in order for this to be useful for spectroscopy or computing vibrational spectroscopy, the frequency has to be set, here it's every 8 steps, which is equivalent to every 4 femtoseconds it will write out to this dump file. So do note that this will consume or will produce a lot of data since you're trying to simulate the spectra. So that's really all we had to change. We just added some new section here to extract those dipoles, and we're just printing out the dipoles here to this dump file. But other than that, it's the same. And then, like the previous example, I'm going to make sure I export the number of threads that's appropriate to my system. Here, I'm going to use all 8 cores I have available. And then I'm going to run the command. Oops, so the command is build lamps, and then we have the in, and then the in.mbx, and this is mbx.h2o. I see it's going off my screen a little bit, but I just added the LAMMPS configuration file here, and then I hit enter. Okay, so the simulation has finished. If I do an ls, I now see I have this new dump.dipoles file, and we can see at the end that it's printed out these dipole terms here, and that's appended them to the end. Something that you might notice off the bat is these zeros, and this is because at the moment how this is constructed is it will print out the dipole for the whole molecule here, and then therefore the other atoms in the molecule will have a zero dipole. So please keep this in mind depending on the kind of analysis you are doing. Okay, but once you have this, if you wanted, you could use this dipole information in order to do the time correlation function and compute the necessary spectroscopy. Okay, and that's actually it for this dipole example. Because it's similar to the pure water example, we're just adding this extra stuff to print the dipoles. And last but not least, we're going to look at our MOF hybrid example. So this is useful if you want to use MBPole or any of our MB energy models in conjunction with some external force field or framework. So I'm going to do a quick check. So MBX.json, this file is normal and is similar to what I discussed previously. Instead, if we look at the initial .data, it's a lot more complicated because for this example, we have our MOF and we have our water molecules here. So you can see that we have a lot more different atom types to describe the MOF, and the atom section is a lot longer. And something you should know is, since this is now a hybrid simulation, do note that in this case, MBX will read the charges for the classical force field model that you're using here. It will not read the charges for anything that is an MB energy model. So like for water, it will ignore the charges for the water molecules, but for the MOF framework, it will indeed read the charges here. So just keep in mind of this inconsistency when you're setting up this input file. And now we're going to look in that input file. Okay, so as I've discussed previously, we have the processors mapped when using MPI as a function of XYZ. We're using real units, atom style full, and periodic boundary conditions. We're reading in the initial .data, and then here we're setting up some groups so that we can keep track of which atom types go to either the MOF versus the water molecule. And note here that the H2O type is 12 for the oxygen and 13 for the hydrogen. Okay, since we have our MOF framework here, we're actually going to specify some bond and angle styles, dihedrals and impropers, and we're going to also specify here now the bond and angle coefficients for the MOF, dihedral coefficients, and some impropers. And then instead for the water, we don't need to specify bond or angle because we're instead going to use what's baked into the MBX library. Okay, in order to get everything to work, we're going to use hybrid overlay. So we're going to overlay a few things here. We're going to overlay MBX with a real space cutoff of 9 angstroms. We're going to use LJ cut, also with a real space cutoff of 9 angstroms. We're going to use cool exclude, which is used because MBX is responsible for computing all of the electrostatic interactions. Cool exclude is used due to the usage of special bonds to make sure that MBX is able to properly handle those special bonds. And then we have some Buckingham here, also set to 9. And the pair modified tail is set to yes here for this example. Okay, here we have even more pair coefficients, and you can see this is for the LJ cut pair type. So those are the LJ cut parameters. Here we've specified some mix parameters. So note that this is between the MOF, which is 1 through 11, with the water, which is 12 and 13. So here we've set some Buckingham and LJs for that mixing between the two types of molecules. And then here on the pair coefficient line, we are specifying to MBX what our system is. Remember that since this is a hybrid simulation, MBX will be computing the electrostatics for the whole system, but some of the pairwise contributions like LJ cut or Buckingham are handled by LAMMPS. So in order to make sure that the electrostatics are handled completely in MBX, we have some added stuff to this pair coefficient line. So note that we're doing star because MBX technically is operating over the entire system and always should be. We're having the pair type here being MBX, and now we're specifying two different monomer types. The first one is DP1, and this is used for these special hybrid simulations. This will pass in the charges of your framework or force field model into MBX so that MBX can compute the electrostatics properly. So remember that the MOF has types 1 through 11. I specify DP1, so the charges from atom types 1 through 11 are passed into MBX. For the second atom type, it is water, so H2O. And since in our system we have it set up so that the atom ordering is OHH, we here specify the LAMMPS atom types of OHH 12, 13, 13. So to recap, we have two different types of molecules as far as MBX is concerned. We have external charges, which in this case is the MOF framework, that are passed in using DP1. And then we have our water molecule with types 12, 13, 13. And at the end, we specify we want the JSON file name that we're reading in to be mbx.json. Okay, the next line here, cool exclude, is something you'll likely need to use if you're doing a hybrid framework, because these hybrid frameworks usually but not always use special bonds. In this case, the special bonds are commented out, so the cool exclude here isn't really doing anything, but for a lot of cases where the special bonds are on, you will need the cool exclude for sure to make sure it's handled properly. So here I'm just telling cool exclude, please operate over atom types 1 through 11, which is the MOF, and if special bonds were on, cool exclude would then operate to make sure that the electrostatics are modified slightly so that the special bonds and 1, 2, 1, 3, and 1 or 1, 4 exclusions are handled properly. Okay. We have our neighbor specification here. Time step here is set to 0.2 femtoseconds per step. We make sure, since MBX is a many-body model, to force it to compute all the pairs and many-body interactions here. And if we want, we can access some of these parameters here if we want to print out, say, like the pip contributions, dispersion, Buckingham, and the electrostatics. But the default thermo output is, the default thermo output happens to have some of these variables like the pip terms being printed out here if you want. Okay, and then we're doing NVT at room temperature here. And we are resetting the velocities on this line. The dump trajectory is commented out. If you want them, you can comment them back in. Restart files are commented out here. We will run the simulation for 100 steps. And if you want, you can turn on writing the data and restart at the end of the simulation. Okay, and just like we did for the previous examples, we're going to make sure to export OMP num threads. Here I've set it to 8, even though it's off the screen. And then we're going to run the example again using the path to our lamps executable, dash in, and then we specify the in file name. Let's see, so dash in dot MBX MOF1H2O. So yeah, that's off the screen a little bit, but that's all you need to do. So we've exported OMP num threads, and now we're going to run the simulation. If you've seen the other examples, since we only have one water molecule, this is of course a lot faster than the ones with significantly more water molecules. Okay, and then now that we're done, we have our new log file generated here. Yes, so we have our log file here. Yep, reproduces all that. We can see the thermodynamic output printed here. And we also get a sense of the performance and total time taken for this example. Thank you for watching this tutorial. Today, we went over 3 examples of how to use MBX with lamps, including a pure water example, a water example where we printed the dipoles, and a hybrid example between MBX and some classical force fields. For more information, please reference our LAMPS documentation, our website mbxsimulations.com, and if you have any unresolved questions, feel free to check out our help forum on our Google Groups. Thanks for watching, and as always, happy simulating!